Hey guys, happy Wednesday. It's our last day together. I know that this hasn't been exactly what everybody thought it would be this summer, but I hope you got something out of this, and that next year your college algebra class is all the better for you having been here. It's a little bit easier, it's a little bit more straightforward, and that some of the concepts that you need to get started, you have a good foundation for, that you're really ready to get going. To end today in this summer session, we're going to be talking about graphing functions and using transformation properties to do so. Now, I won't be using Desmos for most of today, but I will be referencing all 8 of our previous functions. And in fact, we can reference every single function in a basic way using the ideas we're going to talk about today. So let's get started. Here we have 4 of our 8 toolkit functions. What I want to point out about each of these toolkit functions is there's 2 main components to them. There is the variable, which for all of these, the variable is x. And there's a secondary part of these too. There's the operator. The operator is what's being done to the variable. So for a linear equation, what's being done to the linear is you're multiplying to it, or you're adding to it. There's 2 major things that can happen. And the primary one is multiplication, something times x, or something being added to x. For the absolute value is the primary operator. For the quadratic, it's the square. For the cubic, it would be the cube. For the reciprocal, it would be the 1 over. For the reciprocal square, it would be the 1 over x squared. And for the square root, it would be the square root. And so you can see that for each of these, the variable has something that is being done to it. Which means that for today, every transformation we're going to talk about is fitting into 2 major categories. These categories are they happening inside the operator or outside the operator? There's 2 major categories of what can happen. Either you're making adjustments that happen directly to x, meaning they're inside the operator, or you're making changes that are being done to the outside, where you're not affecting x at all, at least not directly. Now let's showcase 2 examples of this. So one example where we're operating inside would be like the square function, like these ones on the top. So moving left and right. So if I was to write something like x minus 4 in parentheses, what goes on the outside would be your operator. So maybe you write x minus 4 squared. This indicates that the square is the operator. And since the minus 4 is inside of the square, it's going to make a change that is in the x-axis. Inside the operator always makes changes with respect to the x-axis. Outside the operator, which would be something like the absolute value of x plus 3. In this case, the absolute value is the major operator. Because the 3 is outside the operator, it makes changes primarily to the y-axis. This can be best illustrated using a pretty basic formula. A on the outside, parentheses, x minus h plus k. These parentheses can be replaced with anything. They can be replaced with just parentheses, making it a linear equation. You could replace those parentheses with a square, making it a quadratic, with a cube, making it a cubic. You could replace them with an absolute value symbol. You could replace them with a square root or a cube root. You could replace that with a 1 over, indicating that you have a reciprocal, or a 1 over parentheses squared, indicating you would have a reciprocal square. But in the end, it would always have this feel. A number times something with our operator inside, we have the x component, and then the k becomes our y component. And that's the big detail we need to talk about today, is how each of these affects the thing differently. The h is going to affect the x-axis. No matter if the parentheses are absolute values, radicals, cubes, cube roots, squares, doesn't matter. H, if it's with the x, is going to affect the x-axis. If it's outside, like the k, it's going to affect the y-axis. And same with the a out here. So let's take a look at Desmos. We're going to take a look at a basic example with a quadratic, and then we'll modify that with a cubic, and the square root, and you can see that this same basic form always holds the same. Now, for a lot of the problems we're going to have today, it may end up being that your graphed version simplifies down to something nicer. But in the end, the big detail is going to be that this form is always true, and when you adjust it, it adjusts it in these predictable ways. Inside always adjusts something on the x-axis, outside always adjusts something on the y-axis. Let's take a look. There we go. So this is your basic ax minus h squared plus k. This is a basic quadratic written in what's called vertex form. Now it's important to note that because a is 1, h is 0, and k is 0, there is a way to rewrite this function as just x squared. If you insert a, h, and k, it's the x squared function. What's really important, though, is what happens if I change these values. Now, because the h is inside of the parentheses with the square, it's with the it's with the x. It's inside the operator, as we call it. And so because it is inside, it's going to only make adjustments that are either left or right, depending on the number. If I chose, for example, a positive number, well, that would make this x minus whatever number we put in. So if I put, for example, the number, let's say 4, like so. Notice how it would become a times x minus 4 squared plus k, where a is 1, k would be 0. So this would simplify to x minus 4 squared. Now because of that, because it is inside the square, it is inside the operator, notice that the only change that was made was that this function moved right. It moved to the right 4 units. Because of where the h is, it is inside of the operator, it only affects the x values. So it takes all of our y's and shifts them either left or right until it makes the new graph. If I move it to the negatives, let's say -3, notice how it just takes my number and shifts it 3 units to the left. That is because if I was to plug this in, this would be x plus 3 quantity squared. So the plus 3 is inside of our square, which again, the square is the operator. It's the big thing happening in the problem. Everything in order of operations, it's first in that list, right? Parentheses, exponents would come after parentheses, so those two come first. And because of that, because it is inside the operator, the only thing the h can possibly change is left and right. That's it. Similarly, put h back at 0 here. If I look at k, k on the other hand is outside of this parentheses. It is outside of the operator of squared. So it will change the y values. But because it is just being added or subtracted, it's going to take those y values and move them either up or down. Let's take a look. If I go to k is 2, notice how it just takes my graph and shifts it up 2 units. Notice because h is 0, none of the x values have changed, right? The bottom of this curve is still at x equals 0. What's happened is the y values have all adjusted. They've all been shifted up 2 units exactly. And so you can actually track point by point what's happened to each value. Example, this point used to be at 0, 0. Now it's at 0, 2. This point used to be at 1, 1. Now it's at 1, 3. Same with the one over here. It'd be at -1, 3. But you can see how they all fit together. They're designed to work that way. Numbers that are inside of the operators always adjust left and right. Numbers that are outside always adjust up or down. And it doesn't matter whether or not this is a square function or any other functions. We'll see in a moment. But before we do that, let's make sure to verify. Yep, if I go down to like -4, -5, boom, there we go. You can see how it took the entire graph and just shifted it down, which means that you can look at every graph of a quadratic not as its individual graph, but as this graph undergoing some changes. Okay? For example, if I want this graph to go through 0 and 3, what I can do is I can adjust some of these pieces until I get them to go through 0 and 3. And when you look at the graph this way, it really changes how you approach math, because you're less focused upon, the numbers themselves, and instead you're focusing upon something else. You're focusing upon, how they fit in the larger scheme. So I want them to go through 0 and 3. Maybe I use, that seems pretty darn close. And so this gives me a rough idea of how I can make my function fit these parameters. But I'm not actually doing any new math. I'm taking this original graph, what we call the Toolkit function, or some mathematicians call it the parent function, and you're just making adjustments to it. You're taking the original function, which was x squared, and you are putting something inside the square to move it left or right. You're putting something outside the square to move it up or down. A, since it is outside of the square as well, will also change the y values, but it changes them in a very different way. Let's go back to 0 and 0. So there's 0, there's 0. If I change A, if I make A bigger than 1, notice how it takes my y values, and it takes that graph and it stretches it up. It takes that graph and it pulls the graph up. It's like you took your image and you're pulling on it like if you've ever messed around with like a picture in a document where you accidentally click on the top and stretched out. Well, that's what it's doing. It's the same picture, it's just been stretched up and down. And notice that it looks like it's just stretching it up, but that's because all of our graph is above the axis. If I move part of the graph down, let's put it back at 1 so you can see this very well. If I move part of the graph down to say here -2, and then adjust this value, it's going to take this graph and it's going to pull it in both directions. It's going to pull the upper half up and the bottom half down. Let's take a look. Good, boom. So you see how it narrows everything out to make sure that it sits in that nice pretty zone. If I make it even bigger still, it's going to keep stretching and stretching and stretching until eventually it gets to that spot. Now, once again, you can track individual values and see how they're changing using A. But all it's doing is it's applying its change afterwards. Notice my x values aren't really changing. It's my y's that are being stretched. And yeah, that forces the x to change a little, but not nearly as much as the y's are because of that stretching motion. If I make this something less than 1, but still positive, so let's say 1/2, notice that it takes my graph, and you can think of it as pulling along the x, but I like to keep it simple. Everything outside the square should affect y's only. So instead of thinking it as pulling on the x, I think of it as pushing down on the y. So everything outside of the operator only affects the y's. So if I have a 1/2 on the outside, it's squishing the y's as opposed to pulling the y's. And so you can see that this graph is the same graph as before. It's just been stretched and compressed or moved left and right. That's all it does. Now, if I somehow go into negatives, notice that when it comes negative, the same rules apply. It's just whether it's upside down or not, because this is a simple flip, where we've taken our picture, and instead of being up here, we've flipped all of our y values to being negatives. Notice that it will flip across the y-axis. So while -2 has those properties, +2 will have the same properties, but every value will be flipped. Instead of being above the axis, it should be below. Instead of being below that -2 on the y-axis, it will be above that -2 on the y-axis. It makes a flip happen. But notice that that point at the bottom, which we call the vertex, is where everything stays consistent. This is where all the change occurs. This point moves either left or right. This point is the starting place for us to either stretch or compress. This point is the place where we either flip above or flip below. And so every single operator can be adjusted just looking at this value. Every other value by comparison is just fluff. It's just taking it and adjusting where this one spot is and how it acts around this spot. Now again, as we said before, this is true at all times for any operator. Now we've shown an example here of where our operator is something being squared. But this is true even if my operator is something being cubed, or even something else. So I'm going to come here. I'm going to make it cubed. Okay. So now, if I take this h value and move it, it should change either left or right. And it will always change predictably, because if I make h x minus a number, it's going to move it, so x minus 2 moves it to the right. Remember, you have to think about where the formula is. It's x minus this number. So this would be x minus 2. Notice it took my graph and it just moved it 2 units to the right. By comparison, if I make this like a -3, when I plug it in, it'd be x plus 3, and that moved it 3 units to the left. Notice that everything else about the graph stays consistent, stays the same. This is always the case, because we're not actually changing our function, we're changing how it looks. Compare this to, if I was to adjust k, so bring this back to 0. If I adjust the k, it just shifts the graph up or down. And again, it's predictable. If the k is plus a number, like plus 3.5, then it's going to move it up 3.5. If it's, the equation minus 2.5, it's going to move it down 2.5. It's predictable. It always acts the same way. Now, most equations are combinations of these things. So you can see how, in this example, this would be the equation x plus 4 cubed plus 3. Notice that it's the same picture, right? If I was to remove the grid, you wouldn't even notice a change had happened. It is just taking that picture and it has moved it 4 units to the left and 3 units up. So if I memorize how this picture looks, I can find how all the other ones look just by shifting it. And if I change the a value, again, that dot isn't going to move there in the center, that vertex, the middle value. This one isn't going to move. Everything around is either going to stretch away, push towards, or flip around it. Example, if I make a bigger, it should stretch this thing out. So notice how my middle value doesn't change, but everything around it does. It gets pulled apart because my number is bigger than 1. If my number is less than 1 but still positive, notice how it kind of crunches it down. Okay? Again, it's affecting the y values. It's making it crunch. If I make it negative, notice that center point doesn't change. It's still 4 to the left and 3 up. But everything has flipped around it to being the other way. I'm practicing my dance moves today, apparently. And that's how it always fits. That's how it always works. And notice how, even though it may look slightly different, more steep, less steep, flipped around, like with the exception of having a equals 0, that's the only place where this function can have a major change happen. Because if a is 0, 0 times the operator will cause it to become 0, meaning it's no longer an operator. It's essentially been destroyed, because 0 doing anything destroys it. Let's put everything back where we started. This works for any function, like, for example, one of our toolkit functions that we do not spend very much time on in algebra, which I think is a shame. There we go. Instead of a cube or a square, or really any power you can do this with, what if I made this into an absolute value? So let's put one here and one here. So notice the h is still inside the operator. In this case, the operator is the absolute value symbol. Now, because it's inside the operator, it's still going to move this left and right. Even though it's a different function, it still moves it left or right. And I can see that right there. My h still moves the function just left or right. By comparison, my k, because it is outside of the operator, will still move it up or down. Because it is outside the operator, all it does is it affects the y values. And my a, again, if the trend continues, it's either going to make it extend away from the axis or away from this center point, or it's going to crush it down towards the center point. But it's affecting y values. That's the big detail. Okay, that center point, that vertex, isn't going to change. It's either going to be pulled from the vertex if it's bigger than 1, or crushed towards it if it's smaller than 1, or flipped around it if it's negative. Let's take a look. See how it the vertex stayed in the same spot, but it just took that thing and just pulled it upwards. If I make it less than 1, but still positive, it takes that graph and it pulls it downwards. Okay, always pulling towards the vertex. If I make it negative, it does the opposite. Just flips the entire thing across the vertex. So instead of being up here, it is now down here. Same vertex, so same center point. Everything is flipped downwards. And notice that if I flip it downwards, h still moves it left or right. That's all h can do. K still moves it up or down. And it does it the same way. If k is positive 4, it still moves it up 4, even when the a is negative. If the h is, negative 2, because when I plug it in, that becomes x plus 2, it moves it to the left 2. And so that fact doesn't change no matter what a is, because it's the vertex. Everything moves around it. Little flapping wings. Boom. And the weird thing is, this works for any operation, no matter how strange or complex. If I was to take this function and get rid of these absolute values, I could take this and put this as 1 over that function. Oops. That's weird. This is the same function. What I mean is it acts the same as it does every other function we've talked about. Let's put them back at zeros. Put a back at 1. A back at 1. There we go. This is a reciprocal function. Notice the h is in the denominator, meaning it is inside of the reciprocal part of the function, right? A is on top. We could also move a out front if we wanted to. So we could write it like this. And it'd be the exact same. It doesn't change that fact, but it's common to write a in the top because remember, when you're multiplying to a fraction, you actually multiply it to the numerator, and a times 1 would be just a. But again, what happens is, because the h is in the bottom, it's in the operator. The operator is the division. Because it is in the bottom, h will move it left or right. So it takes this graph, and if I move h, it just takes the graph and moves the entire graph left or right. Notice it's not changing anything. It's not like the graph is manipulating and rotating something. It's physically picking it up and moving it to a new location. It's like as if you're taking like a clear piece of paper and tracing on it and then moving the clear piece of paper around. All it does is it affects the values. But h only affects the x's. It only moves left or right. K, because it is outside of the fraction, it is outside of the operator, and thereby it only changes the y values. So it's either up or down. And a will either, you can see how this graph also sort of has a center at 0, 0. If I make a bigger than 1, it's going to pull away from that center. If I make a less than 1, but still positive, it's going to pull towards the center. And if I make the a negative, it's going to flip across that center. So let's take a look. Notice how it's taking that picture and just separating it out, pulling it away from the center. If I make a less than 1, but still positive, notice how it gets closer to that center point, and then when it gets negative, it flips the entire graph over. So while the right-hand side used to be the side that was up, and the left-hand side used to be the side that was down, now it's flipped. It's the other way. And this is always the case. Even if I make this a reciprocal squared function, okay? The fact that we have h and k in their very specific locations, either in the operator, so inside of the fraction, inside of the radical, or outside of it, only really changes whether we're dealing with the x values or the y values. We don't change the graph, just how the graph is interpreting the information. Is it interpreting as changing x's? Well, that's because it's inside of our operator. If it's outside the operator, it's going to be affecting the y's. So again, moves it either left or right, moves it either up or down. And the A, again, either pulls towards where we would see as the center of this thing. So the center in this case is 0, 0. For most graphs, when all the other values, when A is 1, H is 0, K is 0, the center is at the origin. That's why the origin is so important. And so it's either going to pull away from the origin, if it's bigger than 1, or towards the origin, if it is smaller than 1. Until eventually it goes negative, and then that entire thing flips over. This is always the case. This is true no matter how complex or unusual your function may be. If you haven't taken a trig class, you can still apply these predictions as long as you know what the graph looks like at the very beginning. Example. Most of you should probably not have taken the trig class yet, but you may not have seen this equation before. This is a cotangent. So this is what cotangent looks like. Cool, right? Makes a nice little artistic pattern. But here's the thing. Because h is inside of cotangent, you may not even know what cotangent is. It doesn't matter. If you know what this graph is, then you should know what h is going to do. Because it is inside of the cotangent, you should know the h is going to take this picture and it's going to move it to the left or to the right. And that's exactly what it does. You should know for a fact that if it is outside of the function, no matter what the function is, no matter what the function is, if it is outside of the function, in which case the k is outside of cotangent, it should move it either up or down. And you should know for a fact that if I change a, it's going to either stretch it out, compress it down, or flip it over. It's the only possibilities. And it's predictable. Even if you have never, ever seen the function before, you should know that much about it. It should always work in this form. But if I take this, see how it's stretching it out? Whereas if I make it less than 1, it compresses it towards the axis. And then if I make it to negatives, how it flips it around. Looks like a very terrible dance in the 80s. All right. No matter what function you are dealing with, this will always be the case, whether you've seen it before or not. Meaning if I pull a random function out, like say, here's one that I can almost guarantee none of you have ever seen before, hyperbolic sine. Hyperbolic sine. If I put the same parameters in x minus h plus k, an a out front, even looking at this, if I adjust a, you should know it's going to either pull it away from the origin or crunch it towards the origin unless it becomes negative, in which case it'll flip it over. You should have a mental picture of what this will do to the graph. And if you do the same thing with h, you should know that if I adjust h, it's going to either move it left or right, and it will be predictable. No matter if you've never seen this graph before, you know that if I adjust h, it's going to move it left or right. If I adjust k, it's going to move it up or down. The trick is learning to see a lot of your math as specifically equations that are being edited in this way. Not as the equations you were given, but as this style of equation, where we're taking the original operator and adjusting it. This is why when I look at an equation like x cubed plus 4x squared minus 3x plus 8, when I look at that function, I don't see the way it's written if I want to graph this. I see it's a cubic, because that's the degree, and the degree is the same as your operator. Because it is cubic, if I can find h, k, and a, I can get a good idea of what that graph will look like every single time. And I never have to worry about, do I plug in 0, 1, 2, and 3? And is that going to give me a good graph or not? Because some graphs don't always act the way you think they're going to. And so you have to be very careful with what your numbers are doing over time. This is going to be it for today. This is going to be it for the entire summer. I hope you guys have enjoyed the class, enjoyed listening to my voice. It's a great voice, I know. Enjoy my dogs playing pool, getting hustled by the fox. But I hope overall that you got something out of this and that your next year is better because of this class. And I will leave you with that.